Hi friends, welcome to this session on selection sort algorithm. We'll discuss about the intuition of this algorithm. We'll also have a dry run for this algorithm and we'll also see the code implementation in Python for this algorithm. So now let's start. So let's say we are given an array which is an unsorted array of size 6, and since it is a zero index based data structure, so the indexes are starting from 0 and ending at 5. Selection sort algorithm sorts the given list by dividing it into two parts. One part is the sorted part and the other part is the unsorted part. Now, for every position of the sorted part, it looks into the remaining unsorted part and selects the minimum element out of that unsorted part and assigns it to that position of the sorted part. And that is where it has got its name as selection sort, because it's based on the mechanism of selecting a minimum element out of the remaining unsorted part. To start with, for the first initial step, it has to look out for the 0th element of the sorted part. The first element. What would be the element at the first position? Now it has to make a selection out of the unsorted part. So what it does is, for the first iteration, it assumes, let's say, this particular part, which is denoted as 40, the 0th element. Let's say this is my sorted part, right? So now for this sorted path, and this is the 0th element of the sorted part. And for this element, I assume that this is the minimum element of this array, and it is at the 0th position. We assume that. So we what we do is we provide it as the the 0 is the index of the minimum element here, right? So the 0th element is the index of the minimum element. Now it will compare with each of those elements which are there in the unsorted part, and the rest of the part, which is here highlighted in green, is treated as the unsorted part for the first iteration, and the one which is highlighted in blue is treated as the sorted part. So we are looking for is the first position of the sorted part. So in the first iteration, what we will do is we'll compare this element 40, which we have assumed to be the minimum element, with every element of the unsorted part. So let's do that. So now what it will do is it will compare the x idx of min, that is the minimum element, whether it is the minimum element or not, right? So it will compare it with the first element of the unsorted part, which is 50. So how does the x of 0, which is equal to 40, compares with 50? Is 40 greater than 50? No, it is not, right? So it will move further. So again, it will check the x idx of, let's say, min, which is, how does it compare with 60 here? So idx of min is x of 0 is equal to 40. And how does it compare with 60? Is 40 greater than 60 or not? It is still not. So it moves further. Again, x idx of min, how does it compare with the next element? 30. So what is x idx of min? X of 0 is equal to 40. How does it compare with 30? Is it greater than 30? It is, right? It is indeed. So what it will do at this point in time, the assumption of ours, where we assume that, okay, this is the minimum element, has been violated. So the index, the minimum element, has been found to be 30, and hence its index, which is 3, would be designated as the index of minimum now, right? So it will be pointing to 3 now, the index of min. So what would happen in the fourth iteration? we now again compare the same thing, x idx of min, how does it fare with the next element, which is 20, and x idx of min, which is now pointing to 3, and x of 3 is equal to 30. So how does it fare with 20? Is 30 greater than 20? It is indeed. So the violation where our assumption was that 30 is the minimum element has been violated. So we will designate the index or identity of index of the minimum element to be pointing to 4. So now here this particular thing in idx of min is now pointing to 4, which is nothing but the value 20. So now in the next iteration, what we will check again the same thing, x idx of min, how does it fare with the another element, the next element, which is 10. Incidentally, it is the last element as well. So x idx of min, idx of min is now 4. X of 4 is equal to 20. How does 20 compare with 10? Is 20 greater than 10? It indeed is. So again, the violation of our assumption that 20 was the minimum element has been violated. So now it will now be pointing it to the index 5, which is the index of the value 10. So the ADX min now points to 5, or the value 10 basically. So since we have now reached the end of the array, we have traversed through all the elements in this particular list, and we have found out that in this particular traversal, the minimum element is at the index location 5. So now at this point in time, it swaps the position. So we started here, which was the sorted part. So now what it will do is it will swap the position 40 with the 10. And now our new list will become something like this. So we have 6 elements, and here we will have now 10. We have 50 here, we have 60 over here, we have 30, we have 20, and here we have got the 40, right? And now our sorted part, basically, which was 10 in or the first element, the sort. So basically in this iteration, first iteration, we have got sorted part of 0 as 10. And in this particular algorithm, at every iteration, that is the traversal through the entire unsorted list, that is one traversal through entire unsorted list, we will get the minimum element out, and we will get uh, the first position or the minimum position of the sorted list. So here we have got in first iteration the number 10, which is the minimum of all the numbers. So we have got the position 0. Now what we will do is, given this particular list, we go into the second iteration wherein we want to see the sorted portion or sorted part first element. So we have found out the second element rather, or the element at the second position. We have found out the first position element. Now we'll find out the second position element. So for this, we move further, and here we assume the element 50, which is at index 1, to have to be the minimum element. So it is the IDX of min. So now what we will do, again same thing. What we will do is we will do a traversal through the remaining unsorted part. So this is the remaining unsorted part, right? So now what we will do in this particular traversal, we'll compare 50 with 60. Is 50 greater than 60? It isn't. Again, x idx of min, how does it fare with the next element, which is 30? Idx of min is pointing to index 1, which is x of 1 is equal to 50, right? How does it compare with 30? Is 50 greater than 30? It is. So the violation of our assumption that 50 is the minimum element is violated. So now we'll move the index of min to the index of element 30, which is 3. So our IDX min has moved to 3. Now in third iteration, what we do, we'll compare with the next element. So x idx min, how does it fare with 20? X idx of min is nothing but 30, or basically the element index of 3 is, index of min is 3, and x of 3 is 30. How does 30 compare with 20? Is 30 greater than 20? Yes, it indeed is. So we will move the index of minimum to now 20. Okay, so we have the idx of min is equal to the index of 20, which is 4. Okay, so now here we will again the same thing, x idx of min, how does it fare with the next element, 40? All right, so x idx of min, x of 4, which is equal to 20, how does it fare with 40? Is 20 greater than 40? No, it isn't. So we have traversed the entire part of the unsorted, or the entire unsorted part, and we have found out the idx of min to be 4. So now here our new swapping that will be done is basically we swap 50 with the idx of min, which is what, 20 right now, right? So we'll swap these two elements. So our new list, our new sorted, or our new list that now becomes, we have 10 as the first element of the sorted part. Now we have 20 as the second element of the sorted part, and we have the third element as 60, fourth element as 30, fifth element as 50 has come over here, and the last element as, which is 40. Okay, so now we have this particular list, and we have at this point in time, this is our sorted part which has been determined. Now we'll move one part further, right? We'll take 60 as well into this, and the rest becomes the unsorted part. So we will do the traversal through the entire unsorted part, and herein our assumption now becomes that 60 is the minimum element. So again, now this is the third iteration, main iteration, wherein we want to find out the sorted parts second, or the second index, or the third position, right? So we have assumed that okay, 60 is a minimum part. So now how does x idx of man compares with 30? So x idx of min, which is nothing but x of, which is 3, 4, 5, right? So it is index 2, x of 2, which is equal to 60. How does it fare with 30? 60 is greater than 30. Yes, it is. So now we'll move our index of minimum element to 30, which is equals to 3. In the second iteration, again x idx of min is compared with the next element 50, and the index of min is 3. So how does x of 3, which is equal to 30, fare with 50? Is 30 greater than 50? It isn't, so it moves further, and now we have the last element 40. So x idx of min, how does it fare with 40? So x idx of min, currently idx of min is designated as 3. X of 3 is equal to 30. How does 30 fare with 40? Is it greater than 40? It isn't. So idx of min is basically, right now what we have got, idx of min is 3, which has remained. So now what we will do is we will make a swap here. Since we have traversed the entire part of the unsorted, or entire unsorted part, so now we will swap the 60 with the minimum element that we have found, and which was at index 3. So 60 and 30 are swapped, and what we get now at this point in time, we get this array, the array sorted like this. we have 10, 20. These were the parts of the sorted. These are the sorted parts, and the third is 30, which is swapped here, came here, and here will come 60, and here will come 50, and here 40. Okay, so this is the list now. So we have determined up till now the three positions, one, two, and three positions of the sorted part, which have already been determined. So now we'll shift to this fourth position. So what we will say, the fourth iteration, main iteration, we are looking for sorted parts position fourth. That is the third index, right? And now again, we assume 60 as the minimum element. So we have the index of minimum as 3. So IDX of men is equals to 3. And now what we do is, let me change the pen. It's looking a bit dull here. So now we have this IDX of 3 as 3. Now we'll compare with 50. So in the first part, okay, so what we have to do, this is the unsorted part. So we'll traverse twice now. So in the first X IDX min, how does it fare with 50? And X and IDX of min is 3, X of 3 is equal to 60. So 60, how did it fare with 50? Is 60 greater than 50? It is indeed. So our assumption that 60 was the minimum element has been violated. So now the IDX min will be shifted to the position 4, which is the element 50. Right, and IDX min is now pointing to 50. Now what we do is the next position, which is 40, the end of the list. So how does X IDX min compare with 40, which is now 50 at this minute? How does 50 compares? 50 greater than 40? Yes, it is. So the IDX of min will be changed to value 5, which is the last one. Now at this point in time, what we do is we again swap these two positions. 60, we were determining for this particular position, the position fourth of the sorted part, 60, and the index of minimum is now 5, which is here. So these two positions are swapped, and we get the list as 10, 20, 30, and here instead of 60, 40 will come, and here 50 will come, and here 60 will come. All right. So up till now, what we have done is we have determined four positions of the sorted part. This one we have already determined. So now we have to determine the fifth position. So we'll go here and assuming it to be IDX of min, right? And what we're looking out for is we have the fourth and the fifth position now. So we are looking for sorted part position number 5, right? And IDX of min we assume to be 4, that 50 is the minimum number, and we have the remaining unsorted part as only one element, which is 60. So herein what we will do is we'll compare X IDX of min. How does it fare with 60? So X IDX of min X of 4 is equal to 50. So how does 50 compare with 60? Now 50, is it greater than 60? It isn't. So no change, and IDX min remains the same as 4. So if there is no change in our assumption of IDX minimum, we do not swap it, right? Because there is no need to swap it, right? Our assumption of it being a minimum element has not been violated. So if we do a swap operation, which basically requires memory writes, which would be an expensive operation, so we might not do that if our assumption of the element being the minimum is not violated. So now at the end of this, So we basically came out with this particular list, which is now sorted 10, 20, 30, 40, 50, and 60. And this is how the selection sort algorithm works out. And as we understood that if the IDEX min violation has not been violated, there is no need to swap it. And also we understood that for for an unsorted array, given unsorted array of length 6, we need to make n minus 1 iterations or one iteration less in order to basically make it a sorted list. Because we have already determined up till point here, right? Are sorted at the end of the fifth iteration. At the end of the fifth iteration, we have determined that this is our sorted part, which is nothing but the size 5. That is the unsorted array length minus 1. So we have already determined it till this particular point. So we need not to move it to the next iteration because the next element is already in its sorted position. So for an unsorted array of length 6, we need to make only 5 iterations to determine or make it a sorted list. So for an index or unsorted list of length n, we only need to make n minus 1 iterations to make it a sorted list. All right, with this, we'll now move into the implementation and the flowchart. So here, as we saw, the selection sort works by repeatedly finding the minimum element from the unsorted part and putting it in the sorted part. The algo maintains two parts, the sublist which is already sorted and the sublist which is unsorted. Swapping is only done once, and that is also if needed in every iteration of the remaining unsorted sublist. Points to ponder, like the time complexity of the selection algorithm is O(n) square, and it makes lesser swaps as we saw. It only does a swapping once it has traversed to the entire length of the unsorted part to find out the most minimum element, and hence is more useful if the memory write operation is expensive. So it does not keep on swapping very frequently as it is being done in the bubble sort, and hence it is much more usable or uh, time efficient, time space efficient if it is uh, the right operation onto which the data structure this sorting is happening. If for that data structure, the memory write operation is expensive. So we start with an unsorted list X. We take a length of it and we traverse through through until the penultimate index. That is, we go until n minus 2th index. That is the penultimate element of the list. As we saw, if a list is of size 6, then we needed 5 iterations to sort that particular list. Then for every or within every iteration, we designate that for that particular position, the element as the minimum element. And then we traverse through the entire unsorted part or the unsorted part of the list to find out if our assumption in which we have designated the minimum element is being violated or not. If it is violated, then we basically make the index of minimum value equals to the value of the minimum element that we have found. If it is not, then there is no change in the index of minimum, and we keep on traversing till we complete the entire unsorted portion. Once that unsorted portion is completed, we make a check if the index of minimum is not equal to I. And what does this mean is the initial assumption of ours, if it is not, if it is violated, that is, if not equal to I, if our assumption has been violated and we have found a new minimum than the one which we had already assumed to be. If it is the case, then we make a swap. If it is not the case, we do not do a swap. This is a bit more optimization on the normal implementations of the selection sort algorithm that you would be seeing. So now it goes on till the entire sorted part is complete. So this is the flowchart. Let's look into the implementation of this algorithm. So we have the selection sort algorithm. We take the initial value of the length of the x, and then we go in from for the value of I till n minus 2 value we go, right? So we have written n minus 1. So since range is not inclusive of the last value, it will go till the I value is equal to n minus 2. We assume the index of min is equal to I. So because this is how we are creating our sorted part. So therefore, for the first iteration, I will be 0, right? Now, similarly, for that assumption of ours, where we are designating the minimum element, we traverse through the entire unsorted part, which is basically which starts from I plus 1 and it goes till the end of the list. And if we see that okay, our violation has been or assumption has been violated, then we designate the index of minimum element as a new value which we have found. And okay, and this print is basically for the demonstration purposes. As you will see, it will help you more to understand when you run this particular code. Now, after the traversal through the entire remaining unsorted sublist being done, if it's all done for one particular iteration, and we see that okay, index of minimum is not equal to I, that is our assumption which we were going ahead with has been violated because it is not equal to I, then we will make a swap, else we will not be making a swap and we'll continue with the next iteration for the next position of the or determine the next position of the sorted part. And this is how the selection sort is implemented. And if I run it over here, and for all of these test cases, this algorithm is run, and this is how it basically shows you. So please have a look at this particular GitHub implementation as well. It is the link to this GitHub repository is available in the description of this video. Please practice it once on paper with a pen and try to see if you are able to write the code, the most optimal code for this selection sort algorithm. In case of any issues, any doubts, any comments, please reach out to me in the comment section from this particular YouTube video. So I hope this selection sort algorithm description and the discussion that we had has been of use to you. Thanks for your patient listening.